Hello, welcome to another episode of What Would You Like to Learn Today? Today I'm going to be explaining to you about stars, so that means you better be ready for some extremely geeky astrophysics. The interesting thing about stars is, we make a big deal about them, and that's because they're so large. They're pretty much the biggest things in the universe, or at least the ones that we see most frequently of the universe at night. And they certainly are very large, but their function is actually very simple. The basic idea of what a star is really, it's an engine that is driven by gravity, and it consumes fuel as it turns lighter elements into heavier elements. Okay? So I want you to imagine, alright, there's a Big Bang, all this stuff gets flown out, kaploom, and there's all these little atoms and molecules that are kind of floating around. Very simple. For the most part, it's just protons, just hydrogen. Okay? So you got all these protons that are kind of they're mostly evenly distributed. They're kind of randomly. It's a cloud, a very diffuse cloud. Okay, but the problem is that because of the Big Bang, there's a shock wave. There's going to be turbulence. Some parts are going to end up being slightly more dense than other parts, and what that causes is a gravitational gradient that kind of draws stuff in towards it. Okay, so stuff gradually starts moving in, and the area becomes more and more dense, more and more protons, more and more hydrogen. Everything is coming together here, and this is what forms what's known as a protostar. Okay, now stuff is coming in, it's forming this whirlpool. It's kind of a vortex, if you will. Think about like water going down the drain. It's spinning around, it's getting more and more dense. Now, as the protons are going into the center of this protostar, what's happening is they're speeding up because they're being drawn into the center, right? Gravity's making them go faster and faster, all right? That means that the temperature's going up. The faster the atoms move, the higher the temperature is. Eventually, enough things have been drawn in here, enough stuff is in the protostar that you get a temperature of 10 megakelvins, at which point that's enough. That's pretty hot, and that's enough temperature for hydrogen fusion to begin. Protons fuse together to make hydrogen 2 to make deuterium. More protons join with those to make... so you get 2 of these guys together, and that makes helium 4. Okay? So what you end up having, originally this is all hydrogen, and then you start producing... It gets really, really dense, okay, and then it starts going, okay? And the hydrogen is being fused at the center into helium. Now, most stars are pretty small, okay? And they keep doing this at that 10 megakelvins for billions and billions of years. Those are called red dwarfs, okay? They're the most common sort of star in the galaxy, and they're pretty cold, but they don't wear out very long, okay? So they go for a while, all right? Now, larger places, now eventually what happens to them is all their hydrogen gets converted to helium. The whole thing is turned into helium, and there isn't enough force then to make that fuse. Okay, so it kind of burns out. It turns into a cinder. Okay. Now, other stars that are larger, what happens to them is, okay, they have a greater supply of hydrogen. So they form that original core of helium, okay, and they don't have enough energy to keep it going, but there is enough force outside here, enough high temperature in the expanding shell to continue fusing hydrogen at a low rate. This is what causes a red giant. It's going to expand out. This is going to happen to the sun, about to the orbit of Jupiter. It's going to swallow up all the planets before Jupiter, probably us also. But we have a few billion years before that happens. Okay? Now, in a larger star, okay, eventually that's going to burn out, and then this will all burn off, and then we'll be left with the core, again, burned out, okay? Now, in a much larger star, okay, what ends up happening is, this is at the outer limit, okay? It's much, much, much larger, okay? It turns out that when it turns all of its hydrogen into helium, it burns out, but instead of burning out, it just draws itself in. It becomes smaller, it concentrates in, and eventually it's able to take that helium and it starts fusing the helium. Okay, originally they fused to make beryllium. Beryllium-8, which is unstable, it usually would degrade, but because there's so much stuff getting fused in here, that fuses with another helium to make carbon. Okay, carbon-12. Now, it'll continue doing that. Eventually, it'll have, you know, so stuff keeps jumping down the layers. The fusion is like now multi-layered. Okay, this will, now the problem is that each time that you step up to a higher level of fusion, there's less available fuel, so it lasts longer, but you burn hotter. Okay, now what ends up happening then, so you've got the carbon-12 core, that's going to continue expanding, expanding, expanding. All right, that'll last you about 1,000 years. All right, the stars can do that for 1,000 years. At that point, everything kind of jumps out. Now you've got an outer layer of helium that's still fusing in to make carbon. And then the carbon begins fusing in to form neon. Okay, now the neon, that'll last you about 10 years, maybe, tops. Okay, and then it does again, it all kind of goes out. Then you have outer layer of carbon, then you've got neon. And then finally, that starts forming into silicon. Now, silicon, everything starts going very, very quickly now, all right? The neon burns into silicon. That lasts you about, I want to say a week. Not even. Maybe a month, tops, okay? You can burn the silicon into nickel. That'll last you a day. After that, you're out of fuel, but you're still really, really hot. You have this immensely dense core. It's all nickel. All right, you can't fuse nickel any further. It's not profitable. You can't get any energy out of doing it. And then you get this really, really, really dense thing forms. Either a neutron star, which is where all the electrons are stripped off and all the nuclei are just packed together. It's really super dense. Or you get a black hole. The outer shell blasts apart. That makes a supernova. The resulting blast wave fuses all the outer layers, and that creates everything that's heavier than nickel. All the elements that we have on the Earth that are heavier than nickel were formed in a supernova explosion such as this. Okay, so that's stars. For the lightning round, I've been asked to explain gang initiation. All right, well, gangs, as we all know, are a terrible blight on American society, but they operate like most primitive social structures in that there's some sort of initiation, right? Now, I don't know. Maybe some of them do like circumcision, or there's like tattoos, or, you know, scarification. Generally, there's a lot of getting your ass kicked, and probably doing some stuff that you don't want to do, and then that like makes you part of the group. You have to do a crime. Anyway, there's lots of variations, but it's usually like being a dick to somebody. Anyway, paper cuts. Paper cuts hurt like bejesus. The reason that they work is because the paper is so thin. It's like as thin as a razor blade, the outer sheets can be, because of how they're cut. It compresses the edges and it makes like a really fine edge, and it takes very little pressure to be able to slice with it. But it leaves fibers behind, and that's why they sting like so much. Okay? Paper cut was also going to be the name of a band that I was going to start with Bill Porter on St. George's Island as part of a movement of literalist ironism. We were pretty drunk. Okay, anchovies. Anchovies, it turns out, are the fish that the ancient Romans used to make garum, which was this sort of fish sauce that they like to put on all of their food. All their gourmands were very into it. But the way that they make it is you take some anchovies, you take out the guts, and you put the guts in a bucket. You leave it out on the docks for a couple of days until it starts smelling just right, and then you strain out the juice, and you put it on all your food, and it tastes great. Anchovies are also bioaccumulators of duomic acid from the tiny shellfish that they eat. And if you get the wrong anchovy, you can get an overdose of duomic acid, which causes shellfish amnesic syndrome. I think it's shellfish amnesic poisoning. Yeah, which basically it short circuits out your short-term memory. So all of a sudden you can't form new memories. Fun, right? Interesting. But they are delicious, and you should get them on everything if you can. Pieces particularly. Lastly, birds on a wire. My grandmother asked me to explain why it is that birds, when they're on a wire, all end up facing in the same direction. And I think this is a good question. I came up with two reasons. Either there's something interesting that they're all looking at, but that would only be happening some of the time. But the real reason, I think, is because they all want to be facing into the wind. They want to be hunkered down. Any wind is going to tend to blow them off, so they want to be as aerodynamic as possible. So I bet they all just end up aiming into the wind, so their feathers don't get ruffled, etc. I bet if you could confirm this on a windless day, check to see if the birds are facing in all directions. I bet they are. All right. Well, I hope that answers everybody's questions. Have a good day, and let me know what else you'd like to learn today.